Imagine standing on a world where the atmosphere is literally being ripped away into space, bathing the surface in deadly radiation. Without magnetic fields, the cosmos is a sterilizing wasteland. But with them, you get oceans, you get thick atmospheres, and you get life. Welcome to The Explainer. Today we're unraveling the most critical, invisible cosmic shield keeping us alive, and we're looking at the groundbreaking science of detecting these force fields, not just in our own cosmic backyard, but all across the galaxy.
To really get why this matters, let's start with a high-stakes cosmic detective story right here in our own solar system. We often think of Earth and Mars as siblings, right? They were both born from the exact same primordial dust and gas. Yet today, one is a vibrant blue marble teeming with life, and the other is a freezing, irradiated desert. So why are we here while our planetary neighbor is dead? Well, the answer isn't just about how far we are from the sun.
It actually all comes down to what's going on deep underground. The difference between survival and extinction is literally buried inside the planet. Earth is massive enough to trap its internal heat, meaning we have this violently active, churning, liquid metal core. That rotating metal acts like a colossal dynamo, generating a robust magnetic shield all around our planet. Mars, on the other hand, formed in a spot where building materials were scarce. It's about 10 times smaller in mass than Earth, so it just couldn't hold onto its internal heat. Eventually, its core cooled off and solidified. Now, about 4 billion years ago, that churning heart of Mars stopped, and when that hot core solidified, its magnetic field essentially pulled the plug. Without that invisible shield, Mars was left completely exposed to the cosmic blowtorch of the solar wind. We're talking high-velocity charged particles from the sun just continuously picking away at the Martian atmosphere. Over billions of years, this unrelenting solar wind completely peeled away a world that once had ocean-girdling ice sheets, rivers, and hydrothermal vents.
The sheer scale of this destruction is kind of mind-blowing. Data from NASA's MAVEN orbiter shows us that, right now, Mars is losing about 100 grams of its atmosphere every single second into deep space. But it gets worse. When the sun unleashes a violent solar storm, which is this massive burst of plasma and energy, that atmospheric escape rate jumps by a massive factor of 10. And because our young sun was way more prone to these extreme solar flares, Mars's atmosphere was likely stripped away incredibly fast early on in its history.
So hunting exoplanet magnetic fields. Since we know these fields are the ultimate unsung heroes of biological survival, the race is on to find them around other stars. If we want to find Earth 2.0, we can't just look for liquid water. We absolutely have to look for the shield that protects that water. And we're entering a golden age of astronomy right now where we're actually probing that invisible armor. We are currently detecting the clearest signs yet of extrasolar magnetism. Instruments like the upcoming Roman Space Telescope are going to hunt for over 100,000 exoplanets, using advanced coronagraphs to directly analyze faint planetary light. Meanwhile, the James Webb Space Telescope is already tracking this really unexpected atmosphere chemistry on extreme gas giants, which points straight to some wild internal dynamics.
Take the so-called impossible planet, TOI 5205b. This is a Jupiter-sized gas giant orbiting a tiny red dwarf star that's only 40% the mass of our Sun. According to our standard models, this planet shouldn't even exist. But JWST peered into its atmosphere and found a bizarre mystery. Its interior is estimated to be 10 times more metal-rich than its carbon-rich outer envelope. That incredible lack of mixing suggests a formation process totally unlike anything we see in our own solar system. It heavily hints that some really complex, deep internal magnetic mechanisms are at play.
And if you thought that was weird, check out TOI 561b. We're talking about a rocky planet whipping around its star in just over 10 hours, with a surface temperature of 3,200 degrees Fahrenheit. It is essentially a wet lava ball. By every rule of physics we thought we knew, this planet should be a bare rock, totally stripped by its star. But JWST data shows it surprisingly maintains a thick atmosphere that actually distributes heat. How is that possible? Well, the intense exchange between that magma ocean and the atmosphere suggests that deep internal mechanisms, likely driven by powerful magnetic dynamos, are constantly burping out protective gases, saving the atmosphere from being instantly annihilated.
All right, let's pivot a bit and talk about probing alien subsurface oceans.
Because, we don't actually have to look light years away to find alien oceans. There are massive bodies of liquid water right here in the outer solar system. To understand how we spot them, we need to talk about magnetic induction. This happens when a fluctuating external magnetic field generates electric currents in secondary magnetic fields inside a conductive body. Jupiter has a monstrously powerful magnetic field. As its icy moon Europa orbits through that field, the magnetic energy induces electric currents deep inside the moon. And what conducts electricity really well? A massive, salty, churning subsurface ocean. Europa's induced magnetic response is the ultimate giveaway, proving that a saline-rich ocean is hiding right beneath its 100-kilometer-thick ice crust. So how do we actually measure this? Well, NASA's Europa Clipper mission is basically setting a giant magnetic trap. First, it uses an instrument called PIMS to isolate Jupiter's noisy plasma currents, which normally drown out Europa's weak signal. Then, it drops the ECM, a highly sensitive magnetometer, on this massive boom to catch Europa's faint, induced signal over multiple close flybys. Finally, by crunching all this incredibly precise data, scientists can calculate the ice shell thickness, the ocean depth, and even the salinity of the water. This magnetic data is literally the key to confirming if Europa has the exact right conditions to harbor life.
Moving on to relics of ancient magnetism.
These fields aren't just real-time shields, they're also essentially ancient recording devices that lock away the violent history of our cosmic neighborhood. Take our moon, for example. The moon's magnetic history is a complete mystery that totally defies our models. 4.5 billion years ago, when the moon was molten, it supported an active magnetic field. Theoretical models told us that as it cooled, that dynamo should have completely shut down around 3 billion years ago. But when astronauts brought back rock samples from the Apollo 15 mission, scientists were shocked. The magnetic field somehow hung on until just 1 billion years ago. We still have no idea how our small, dead moon maintained its magnetic dynamo billions of years longer than it physically should have.
To really unpack these ancient mysteries, we have to go back to the original building blocks of the planets themselves. That's exactly why NASA's Psyche spacecraft is en route to an ultra-rare, metal-rich asteroid named 16 Psyche. Scientists actually believe this asteroid might be the stripped-down core of a destroyed early planet. By using its onboard magnetometers to directly measure the asteroid's remnant magnetic field, Psyche is going to give us an unprecedented look inside the iron heart of a world. This is crucial for helping us understand how these magnetic dynamos even form in the first place.
And finally, let's look at extreme magnetic cosmic phenomena.
Because when you scale these fields up to the absolute extremes of physics, you get the most terrifying objects in the cosmos, magnetars. These are ultra-dense neutron stars, born in the explosive death of massive stars. If the dying star's core has the perfect initial rotation, it spins up an internal dynamo that ramps its magnetic field beyond the extreme. We were talking about the most powerful, universe-shaking magnetic fields ever discovered, literally millions of times stronger than anything we can produce in a lab. And they're highly volatile. When the crust of these ultra-dense stars shifts in what we call a starquake, the magnetic field violently glitches. This unleashes a blinding burst of electromagnetic energy, dumping an entire sun's worth of power into deep space in the blink of an eye.
But hey, these magnetic extremes aren't just confined to dead stars. They exist in the very fabric of the space between stars, too. When NASA's Voyager probes finally pushed out of our solar system and into interstellar space, they made a massive discovery. The interstellar magnetic field out there is actually 2 to 3 times more powerful than theoretical models previously thought. This means that the charged particles in interstellar space are constantly exerting this immense, crushing pressure on the boundary of our own heliosphere, which is the protective magnetic bubble generated by our sun. It turns out we are sailing through a highly magnetized, incredibly turbulent galactic ocean.
Which brings us to the million-dollar question. Knowing that magnetic fields are the vital cosmic shields holding on to atmospheres, protecting oceans from solar blowtorches, and regulating planetary climates, is detecting alien magnetic fields the ultimate missing key to finding extraterrestrial life? As the next generation of space telescopes hone in on these invisible signatures, we're no longer just looking for rocks in space. We are looking for safe harbors. And finding them might just answer the biggest question in human history. Are we alone? Thanks for joining me on this explainer, and keep looking up.